I've been busy writing chapter 19 of Kotlin an Illustrated Guide, and this chapter is going to cover generic variance in Kotlin. So in other words, explaining why an array of integers is not a subtype of array of numbers. And I think one thing that's often overlooked is that variance doesn't only apply to generics, it actually applies to regular type hierarchies as well. In fact, I think that by understanding how variance applies with just normal type inheritance and type hierarchies, we'll get a better understanding of why variance applies to generics as well. So let's jump in. In most cases, a type contains one or more associations to other types. And to show you what I mean, I've got here an interface called vending machine, and it associates with two other types. So it's got a parameter type here, which is coin, and it's got a return type here, which is snack. So in other words, it's a vending machine, you put in a coin and you get a snack back. Variance describes the nature of the relationship between the container type and one of those associations that it contains. So for this interface, variance can describe the relationship between the vending machine and this parameter type, or it can explain the relationship between the vending machine and this return type. So if we were to create a class that implements this interface, we could just keep these associated types exactly the same as they are in this interface. And I think most of the time that's actually probably what we do. So in other words, if we create a subtype, the parameter type would still be coin and the return type would still be snack, just like they are in this interface. But it doesn't have to be this way. These associated types can climb up or down their type hierarchies depending on where they are in this container class, as long as we uphold the contract, which is that this purchase function must always accept a coin and return a snack. So in other words, as long as the subclass or the subtypes of vending machine still accept anything that's a coin and return something that's a snack, everything's good. To demonstrate this, let's start with the return type, which is snack. Let's assume we have a type hierarchy that looks something like this, where the snack.random function can return either a candy bar or a bag of trail mix. So if this subtype, simple vending machine, if it were to always return a candy bar, would this function still be returning a snack? And it would, because candy bar is a kind of snack. So instead of snack.random right here, we could just instantiate a candy bar directly. And we can also change this return type to candy bar. So in other words, just like simple vending machine is a subtype of vending machine, candy bar is also a subtype of snack. So as this container type becomes more specific, so can this return type. And since they become more specific together, we call this covariance, where the prefix co means together. Now, I've only got one function in this example, but covariance applies to the return type of every function and also to properties that are declared with the val keyword. Now, this doesn't work the other way, so we can't replace it with a type that's more general. So let's say that snack derives from another type called product, and product includes both snacks and toys. In that case, we can't declare that this returns the product type. And why is that? That's because the contract said that the vending machine will accept a coin and return a snack. And if it returns toys instead of snacks, some poor kid is going to end up breaking his teeth trying to chew an action figure or something. So Kotlin prevents us from doing that, and it gives us this compiler error instead. So let's put this back. So to summarize before we move on, the relationship between a container type and one of its return types is called covariant, because as the container type becomes more specific, so can the return type. Now, what about the parameter type here? Can it also become more specific in subtypes of vending machine? Well, the contract says that this function must accept any kind of coin and return some kind of snack. So if we were to declare a more specific type here, like a quarter, then it would break its contract. Now, sure, a quarter is a kind of a coin, but it has to accept any kind of coin, including dimes. And so if we declared that it only accepts quarters, the people who have dimes wouldn't be able to get their snack. So it would not be type safe to allow that here. And what about a more general type? What if this machine could accept any kind of money, including either a coin or a bill? Since this money type still includes all coins, it'd be perfectly type safe to allow this. Now in Kotlin, we can try to do this, but we'll get a compiler error saying that this function doesn't override anything. So even though it would be type safe to allow a more general type here, Kotlin is not going to allow it. And the reason for that is that Kotlin supports function overloading. So in other words, we can remove this override keyword here, and that would make this function an overload rather than an override. And that would fix this error. We would still have to implement the missing function though, in which case we would be juggling two function bodies, and that's not exactly what we want. So just to reiterate, from a type system perspective, it's totally fine to allow a parameter to have a more general type in the subtype of the container. It's just that we can't do that in Kotlin because of function overloading. But you know what you can't overload is properties with a function type. So let's change our interface from having a function to having a property with a function type. And in our class, we can just change this to a property with a lambda. And now we can change this coin type to something more general, like money. And as we can see, it compiles just fine. So simple vending machine is a subtype of vending machine, but money is a supertype of coin. So in other words, as the container type becomes more specific, this parameter type can become more general. Since they become more specific in opposite directions, we call this contravariance. We only have one type parameter in this example, but again, this holds true for all parameters in the container type. So we can summarize our findings like this. Within a subtype, return types can become more specific, which is known as covariance, and parameter types can become more general, which is contravariance. And now that we've seen variance apart from generics, it makes a whole lot more sense why generic variance works the way that it does. So let's take a look at this vending machine interface where I've converted it into a generic. When a type parameter is declared without, it can only publicly appear as a return type, which as we've seen means that the container type can have a covariant relationship with it. And when a type parameter is declared with the keyword in, then it can only publicly appear as a function parameter, which also, as we've seen, means that the container type can have a contravariant relationship with it. So given two parameterized types, we can look at their type arguments. And as long as the one whose type parameter is marked as out is the same or more specific than the first, and as long as the one whose type parameter is marked with in is the same or more general than the first, then the contract isn't broken and it's perfectly type safe for the second to be a subtype of the first. And there you have it. Variance without generics can help clarify why variance works with generics. Good job working your way through all of the content in this video. As I said earlier, you'll be able to read a lot more about this when chapter 19 of Kotlin an Illustrated Guide comes out. In the meantime, keep experimenting with this stuff, keep coding, and of course, feel free to reach out to me in the comments section or on social media with any thoughts, ideas, or questions you've got. See you next time. You've read the chapters online, and now I'm proud to present the Lean Puff edition of Kotlin an Illustrated Guide. Take the book offline with you, mark it up in your favorite PDF software, and get early access to new chapters as they're written. You can pick up your copy today. Just go to book.typealias.com.